right, we're going to now look at the design of a double angle 2L4 design strength of a double angle long legs back to back. And first thing I want to talk about is first thing we want to calculate is the if I want to use the design tables, is the effective length, because that's what we can use in the design tables, right? Well, right now, K equals 1.0 because it's pin, right? Pin. And my LX equals my LY equals 8 feet, right? It doesn't say that there's any intermediate bracing. So my LCX is equal to LCY is equal to 1 times 8 feet is equal to 1. Okay, so now I can enter the design tables. I am looking for 2 L4 by 3.5 by 3/8 long legs back to back with a 3/4 inch separation and ASTM A36 steel. Okay. Let's go to my design tables. So let's see. If you go to page 4 by... Oh, these are equal. That's why. I was like, wait. Okay, there we go. Long legs back to back. Okay, so let's see. We have A36 steel, okay. 4 by 3.25 or 3.5. Long legs back to back. 3/8 L4 by 3.5 by 3/8. And I want to go to 8 feet. And look, it's effective length with respect to 2 different axes. This is respect to X. Right, we have our x-axis, 8 feet, 127 inches, or kips, I'm sorry, and 8 feet for the y-axis, 130 kips. Now, is that the same? I thought I saw it was slightly different. Right, so you should be on page 4-158. 127. It's 132 in the 15th edition, not 130. 4 by 3.5, 3/8, 132. So let's just say that, right? 132 kips in 15th edition. It's still 127 for the y-axis. I don't know if there was a typo or what, but the one thing that you'll notice is there's an assumption. Right here. It says 3/8 of an inch. Right, if you go back to the beginning of the chapter, it'll probably tell you a little bit more. It doesn't, but what it's telling you is property of two angles 3/8 inch back to back, which means assumes a separation of 3/8 of an inch is what that means. Okay. Well, let's go back to our design. It said 3/4 inch, right? Right. I have 2L 3.5 by 3/8 check, long leg back to back check, ASTM A36, but I don't have I have 3/4 inch separation, not 3/8. So what does that mean? It means if I'm looking at my angles, these are long leg back to back, although it's not that different, but the separation between the two is 3/4 of an inch. But table assumes 3/8 of an inch. So what does that separation affect? Well, if we go back and look at this little picture right here, we have an X and a Y. Should be looking right in front of you, but we have, this is our centroid, our X-axis, and our YY axis, right? XX and YY. If I make my angles further apart than they are assumed, will it affect the XX or the YY properties? Increasing separation affects are my YY properties. For example, my RY. So that means that if I go to my design table, this is probably fine. This 127 is probably fine because my x-axis doesn't depend on that. But my y-axis, this might change. So this is similar to an equivalent length when we have strong versus weak axis bending in the in the W shapes, right? When we have to calculate different equivalent length. So what I'm going to do is I'm going to calculate slenderness ratios for my X and Y and see which one actually controls, right? So I need to know my RX and my RY for the two different setups. So I'm going to go to my dimension tables. Okay, double angles. Those are short legs back. That's long legs back to back. This might look a little bit different. I'm on page. Yeah, it's broken up. No, it's not. It looks the same. Okay. Might look a little bit different, but okay. You're on page 1-114. So here I have 2 4x3.5 3/8. And my radius of gyration, I have 3/4 of an inch separation, long leg back to back. My radius of gyration for that separation is 1.69. So my RY is 1.69 inches. That's for my 3/4 inch separation. My RX is 1.05. Nope, that's short legs back to back. Is one. See, long legs back to back. My RX. All right, there's RX 1.25 inches. So you see the RX doesn't depend on the separation. Which makes sense, right? The further thing, if a dimension changes in the Y direction, if a dimension changes in the Y direction, right, this increased the dimension like this way, right? So the change would be in the Y direction, not the X direction. So let's see. My RX was 1.25 inches. So let's see. KL over R. For my X is 1 times 8 feet times divided by 1.25 inches. KL over R. Y 1.25 inches over, no, I'm sorry, 1 times 8 feet divided by 1.69 inches. So this actually is going to help us out. Right. So 8 divided by 1.25, 6.4, 8 divided by 1.69, 4.73. So in this case, that slenderness ratio controls. Therefore, I can use $127 kips right? My 4 by 3.5 by 3/8, 8 feet, 127 kips. Because my slenderness in the X direction was larger, I can use that value. So that is on page 4-158, table 4, table 4-9, LCX equals 8 feet. If my Y had controlled, then I would have had to have done an equivalent length to correct that. And you might see that in the design example. But actually by doing this, right, well, I'll show you what they do in the design example. What they do is if LC, or if KL over RY was larger and controlled. Now remember, LCY in table 4-9 assumes a separation of 3/8 of an inch. So we're going to have to do an LCY equivalent and make the slenderness ratio, right? If you would do KL over RY actual, right? That would be kind of like this one. To some KL over RY equivalent. And then you basically solve for, right, LY actual over RY, our actual RY, LY equivalent over RY equivalent. LY equivalent is to be used in table 4-9 where RY equivalent is assumed to be RY for a separation of 3/8 of an inch. We have an actual separation of 3/4 of an inch. So we want to solve for that equivalent RY equivalent over RY actual. We want to, this is similar to what we do when we're converting from weak axis, finding that equivalent length if we actually have strong axis bending in a W section. We want to find an equivalent length that would give us the same slenderness ratio, is what we're doing. We want to have the same slenderness ratio. So we need to calculate a length that would have the same slenderness ratio, but with a different RY, is basically what it is, right? Same thing for weak versus strong axis bending. You want to find an equivalent slenderness ratio that assumes with RY versus a slenderness ratio with RX. So this is same in here, right? Let me see. We can substitute, right? Let me write a different color. Similar to LY equivalent equals LX divided by RY over RX. Or RX over R, yeah. Oh, I did it wrong, that's why. Okay. RX over RY. And this would be equivalent is equal to RY actual over RY equivalent. Right? Replace actual with X and equivalent with Y. I took the wrong things to the wrong side. I hope I didn't. Right. I took this. Oopsies. Right. I just divided this by RY equivalent. So that this goes away. And the RY equivalent is the RY for a separation of 3/8. The RY equivalent is what is assumed in the table. For W sections, assumed in the table is RY. And what you actually have is RX. For a W section, so this would be LY actual is, or LCY, I guess, LC. LCY equivalent is LCY actual, which is 8 feet, divided by our actual RY, which is our RY for 3/8 of an inch, 1.69 in, or 3/4 of an inch, I'm sorry, which is 1.69 inches, and our RY equivalent, you can look at it in the actual 3/8 of an inch, 1.55 inches instead of the 1.69. See, the 1.25 is the same, 1.55 is different. So that would give you an equivalent length to use in the table of about 5.9 feet. So that means it actually, right? So it's about 6 feet. Now, I don't know about you, but if something gets shorter, it's probably not getting any, it's probably getting stronger when it comes to, we probably just increase its strength because buckling is all about how long and slender something is. So now if we just assumed it's shorter, it's probably not going to gain any strength, right? So let's see, about 6 feet for the Y. Now we've assumed a Y equivalent, right? We're still looking in the Y. We're not back up in X, but 6 is 144 kips. This is for our LY equivalent of about 6 feet. So still 127. Right. What that means is this is going to buckle in about the XX axis before it buckles about the YY axis. It was going to do it if the separation was 3/8 because 127 versus 130. And increasing that separation increased the radius of gyration, which decreased the slenderness in the YY direction. And it's about 144 kips. So x-axis buckling controls VCPN equals 127 kips. Right? Because it's going to buckle in the x-axis at 127 kips before it can even get to that 144. This is because KL over RX is greater than KL over RY. And let's see, RY for 3/8 of an inch was 1.55 inches. RY for 3/4 of an inch separation, right? You increase the separation, you increase that RY. Therefore, KL over RY decreased. Right, therefore, KL over RY decreased with your increasing separation. Making 2L 4 by 3.5 by 3/8, even more likely to buckle in X direction first. Have X-axis controlling, if that makes sense. I'm just kind of writing it down, right? Because if you look at it again, 127 for 8 feet, 127 kips for 8 feet in the y direction, 130 kips. Already your x-axis is controlling. Increasing that separation only increased the radius of gyration, which decreased the slenderness ratio, which means it made it even more likely that it was, right? It went from 130 to 144. Now it's not even close. It's gonna buckle in the x-axis, what is that, 17 kips earlier. So I hope that kind of made sense. So you can look at that on the axis, on the examples if you would like. Oops, I forgot to